narration script for slide 1. Greetings, students. Today, we delve into an intriguing challenge from LeetCode, specifically problem 128, titled Longest Consecutive Sequence. This problem invites us to explore the fascinating world of consecutive integers within an array. Imagine we are presented with an array of integers, which may encompass both positive and negative values, and indeed may contain duplicates. Our objective is to identify the longest sequence of numbers where each integer follows the previous one in a consecutive manner. For instance, consider the array 100, 4, 200, 1, 3, 2. Here, the longest consecutive sequence is 1, 2, 3, 4, which consists of 4 elements. Hence, our expected output is simply the integer 4, representing this maximum length of consecutive integers. As we embark on solving this problem, let us sharpen our analytical skills and deepen our understanding of algorithmic design. Hashing with a set is a powerful technique for managing collections of unique elements. Imagine you have a box where you only want to keep one of each type of toy, and this box automatically prevents duplicates. This is essentially what a set does. When we use hashing, we take each element, like a toy, and apply a hash function. This function converts the toy into a unique number called a hash code. This number tells us where to place the toy in an underlying array. Because of this system, we can quickly check if a toy is in the box, add a new one, or remove one, all in constant time on average, which is much faster than searching through a list. However, sometimes 2 toys might get the same number, a collision. Sets handle this with methods like chaining or open addressing to keep everything organized. This combination of hashing and sets gives us an efficient way to store and manage unique items, making it invaluable in applications where speed and efficiency are critical. Let's dive into the function we see on this slide, which finds unique elements in a list using a set. First, we initialize an empty set called unique elements. Think of a set like a special box that only holds unique items, no duplicates allowed. Next, we loop through each item in the input list. For every element, we add it to our unique elements set. If an item is already in the set, it simply won't be added again. This is the beauty of using a set. It automatically filters out duplicates for us. Finally, we convert our set back into a list and return it. This gives us a list of unique elements. In our example, when we pass the list 1, 2, 3, 4, 4, 4 to the function, we get the output 1, 2, 3, 4. So we efficiently eliminated the duplicates. This method is quick and effective, making it a great choice for handling lists when we need unique values. A frequency array is a powerful tool for counting occurrences within a collection, like an array or a list. Think of it as a scoreboard that tracks how many times each element appears. Each index in this array corresponds to a specific element. So, if we have a collection of numbers, the index represents the number itself, and the value at that index shows how many times it occurs. To create a frequency array, we start by initializing an array filled with zeros, sized according to the range of possible values. As we go through our original collection, we simply look at each element and increase the value at its corresponding index. This process allows us to tally counts efficiently in just one pass through the data. The beauty of frequency arrays lies in their speed and efficiency. They enable quick lookups and can significantly cut down the time it takes to analyze datasets. They're especially handy when working with a known, limited range of input values, such as counting characters in a string or integers within a specific range. This method transforms potentially slow counting operations into swift, efficient solutions. The function we see here creates a frequency array from a list of numbers. Think of this frequency array as a way to count how many times each number appears, like tallying votes in an election. First, we initialize an empty dictionary called frequency. This dictionary will hold our number counts. In Python, dictionaries are great for storing key-value pairs, where the number will be the key and its count will be the value. Next, we loop through each number in the input list. For each number, we check if it's already in our dictionary. If it is, we simply increment its count. If it's not yet in the dictionary, we add it with a count of 1. Finally, we return the completed frequency dictionary. This function is essential for problems like finding the longest consecutive sequence, since it helps us understand how many times each number appears, giving us the foundation to build upon for further analysis. Iterative traversal for sequence checking is a key concept in computer science. Imagine you have a row of boxes, each containing a different item. To find out what's inside, you would open each box one by one. This is essentially what iterative traversal does. It examines each element in a sequence, like an array or a list. Using a loop, we can systematically access each item. We start at the first element, check its value, then move to the next one and repeat this process. This method is incredibly useful for tasks like searching for a specific number or checking if the items are in the correct order. The power of iterative traversal lies in its versatility. It forms the backbone of many algorithms, whether we're sorting data or searching through it. By mastering this technique, you're equipping yourself with a fundamental skill for effective data manipulation and algorithm design. Remember, each time you traverse a sequence, you're not just moving through data, you're also building a deeper understanding of how to work with it efficiently. This slide prints a function called double sequence, which is designed to double each number in a list. Let's break this down step by step. First, we see the function definition. It takes an input, which is a list of numbers called numbers. The goal here is to create a new list that contains each of these numbers multiplied by 2. In step 1, we initialize an empty list named doubled. Think of this list as a container where we will store our results. Moving on to step 2, we use a loop to go through each number in the numbers list. As we do this, we take the current number, double it, and then add that doubled value to our doubled list. Finally, in step 3, we return the doubled list, which now holds all the numbers from the original list, each one multiplied by 2. This process illustrates how we can transform data using simple operations in programming. It's a clear example of how iterative traversal works, making it easy to manipulate sequences. To solve LeetCode problem 128, we need to find the longest consecutive sequence in an unsorted array of integers. Let's break down the solution step by step. First, we should understand the problem context. We need a sequence of consecutive integers, like in the array 100, 4, 200, 1, 3, 2. Here, the longest sequence is 1, 2, 3, 4, which has a length of 4. Next, we choose a hash set as our data structure. This allows us to efficiently check for the existence of numbers, which is critical for finding those consecutive sequences. We start by inserting all elements from the array into the hash set. This gives us quick access to check if a number is present. Then, we iterate through each number in the set. For each number, we check if it's the start of a sequence by ensuring its predecessor isn't in the set. If it is the start, we count the consecutive numbers by checking num plus 1, num plus 2, and so on until we hit a number that isn't found. As we count these consecutive numbers, we keep track of the maximum length found. Finally, we return this maximum length. In terms of performance, this approach runs in O(n) time, where n is the number of elements in the array, making it efficient. The space complexity is also O(n) for storing elements in the hash set. This method effectively finds the longest consecutive sequence in a straightforward and efficient manner. In this problem, we are tasked with converting a string representation of an integer into its integer form, while adhering to specific parsing rules. Key constraints include handling leading whitespace, recognizing optional plus or minus signs, and correctly processing invalid characters. Notably, the output must be clamped within the bounds of a 32-bit signed integer, specifically between -231 and 231-1. The function should terminate parsing upon encountering a non-digit character after initial whitespace and sign processing. The function myAtoy is designed to convert a string that represents an integer into its actual integer value. It starts by using else strip to remove any leading whitespace, which is crucial because extra spaces can interfere with the conversion. If the string becomes empty after this step, the function returns 0, handling invalid input gracefully. Next, we introduce a variable called sign, which is set to 1 by default. This variable will help us determine if the final integer should be positive or negative. The function then checks if there's a sign indicator at the start of the string, adjusting the sign accordingly and moving the index forward. The heart of the function is a while loop that processes each character to confirm if it's a digit. For each valid digit, we construct the integer using a base 10 accumulation method. This means that we're essentially building the number by multiplying the current result by 10 and adding the new digit. After the loop, we apply the sign to the result. Additionally, the function checks to ensure that the final integer fits within the 32-bit signed integer limits. If it exceeds these bounds, it returns the appropriate cap values. This methodical approach combines input validation and boundary checks, ensuring that our solution is both robust and efficient. The time complexity of the longest consecutive sequence problem is O(n). This means that we can solve the problem efficiently, processing each element in the input array at most twice. First, we add each element to a set, which allows for fast lookup times. Then, when we check each element to see if it's the start of a new sequence, we're again processing it in constant time. Next, let's talk about space complexity, which is also O(n). This is because we use a set to store all unique elements from the input array. In the worst-case scenario, this set may need to hold all n elements. Think of the set as a container where we keep track of what we've already seen, ensuring we can efficiently determine if a number belongs to our sequence. By understanding these complexities, we can appreciate how our approach balances speed and memory usage, making it effective for this problem.